Wow. Okay. Uh, this is our last week of meeting. We're gonna talk about basics of the basics of statistical learning today, and then on Thursday about principal component analysis, which is closely related to the singular value decomposition. So this would be from a point of view of how statistical learning and numerical linear algebra overlap, and what concepts that we've seen already have been used in this area. And when I was looking at this stuff some years ago, I got a book on statistical learning, and the book is mentioned in the notes. It's actually freely available online. Well, it's probably kind of out of date by now, because the field is changing so rapidly. But I was actually surprised to see how much of an overlap there is between, like, I guess, more classical numerical methods and like machine learning, because people talk about machine learning as if it's some new thing, and it's more about the packaging that's new than the mathematical substance. So someone who has a lot of training in numerical analysis, it may not be very difficult for them to pick up machine learning type things and concepts. But of course, I'm going to put that to the test, because for my summer or for this summer for NRL, I'll probably be dealing with that sort of thing, neural networks and so forth, and we'll see how easy it is to pick all that up. But anyway, okay. So, okay. Right. So the situation that we have here is simple to describe. Okay. All right, so we have our output y, our input x. Okay, and suppose that our input and output have this kind of relationship, and epsilon represents our error, and this is treated as a random variable where the expected values of the error is 0. Okay. So, in a nutshell, statistical learning is about like the function f is unknown. But we have some sample inputs and outputs, x and y. We can use those to try to get a handle on what f is all about, and how to at least approximately evaluate it at data other than what we already have. Right. Okay. Now, as far as I need to drop a lot of terminology on you. Okay. So x and y are referred to as not just input and outputs. X is often a vector value quantity. And is referred to as okay. Of course, you know of x as independent variable, also known as predictors. Like each of these individual components of x are referred to as independent variables or predictors. And then y, as you know, is referred to as a dependent variable or a response. All right. All right, so as okay. Was a real world example of this kind of relationship. Most of our data consists of the following. We have, okay. So suppose we have sales of a certain product in 200 different markets. And suppose we also have data about the ad budget in each of these markets. But the ad budget breaks down into categories. We have TV, radio, newspaper, obviously a very 20th century example. Okay. So what we can do is so that we can think of the these ad budgets in the different markets as the predictors, and the sales are responses. So we want to get a handle on what is the relationship between advertising budget of various kinds and sales, so that we can determine where to put our advertising dollars to get the strongest response. Well, that is most sales. Okay. I also like, I'm dehydrated. How do you water?
You already defend your master's thesis.
No. Yeah, I didn't do a master's thesis. I had to do opportunity kind of. No, that was at a different school.
Okay. Now, there are two particular purposes to understanding F. I'll talk about prediction and inference. Okay. All right, so starting with prediction. So if F itself is difficult to evaluate for a given X, maybe it's computationally expensive. So you'd like to have an approximation where y hat is equal to some function f hat of X. So we still have our same input, whatever data we have. So hopefully our f hat is an approximation of f, so that our y hat will be a decent approximation of what a true y would be. I mean, keep in mind, f is not entirely known anyway, because we have that error term epsilon that is we can never really know. Okay. All right. Okay. So in this case, y hat is serving as our prediction of what y would be. We already have some data, like some XY pairs, that give us some information about the underlying function f. But what if we have some other inputs x that we want to know the corresponding y for, and we may not be able to get that easily. If we can concoct an approximate f hat from the data that we have, then we can use that to figure out other XY pairs. Okay. All right. All right, so as a real life example for this, so suppose we have our predictors x1, x2, up to xp. Well, their characteristics of patients' blood samples. All right, so each one of these x's is a characteristic of a particular sample. So we might have several blood samples, and for each one of them, we have an x and the components of x. Are those characteristics for that patient. Okay. And let's suppose that y, in this case, it represents the risk of having a severe reaction to some drug. Okay, so we like to measure a patient's risk based on their what we know about their blood sample. Okay. Okay. So the goal is to estimate y before giving the drug. So that if it turns out that the measured y is high, then we can just not give it to them. So we may have, from a clinical trial, for instance, several XY pairs from patients on whom this drug was tested, and gathering data on who had severe reactions, so that for patients not involved in the clinical trial, we can use the data that we have to assess what the risk would be based on a blood sample, and hopefully not put them at risk. Right. Now, if we're going to approximate our unknown function f with some function f hat that we can evaluate at any x, of course, we have to be concerned about error. And there's two types of error. Okay. So first is reducible error. So you think of it as f hat minus f. All right, so it's the difference between them, in measured in whatever way, like you want to use a norm or something like that. And it's called reducible error because your approximate f hat, you have the potential to make it more accurate. By choosing the right form of that. Like, for example, if you're using polynomial interpolation, you can try using the higher degree polynomial, for instance, to make this error smaller. Maybe there's some fine tuning of your regression technique that you can use to make it start smaller. So it's something you have some control over. And if you're lucky, you might be able to make f hat equal to f. If that's not the norm, but pun not intended. But it can happen depending on how simple the relationship is between your x and y. Okay. The irreducible error that is epsilon, right? We don't have a handle on that. There isn't really anything we can do about it, unfortunately. Okay. Because when we say that y depends on x, well, y may depend on other things too. And we don't have those accounted for in f, because f is a function of only x. So those dependencies, they may not be the strongest dependencies, but they're incorporated into epsilon. And since we don't have that accounted for in our data, we have no way to mitigate that. All right. So what I can do is to look at the expected value of our true outputs y minus our predictions y hat. So really looking at the variance here, looking at the expected value of a difference squared. Okay, so what I can do with that is if I just substitute in what y and y hat are, well, y is f of x plus epsilon, and then y hat is f hat of x. Okay. Okay. And with a lot of manipulation, well, it's not a whole lot, but some manipulation is carried on the notes, and using the fact that the expected value of epsilon is assumed to be 0, what we end up with is x minus f hat of x squared, and then what's left is the variance of epsilon. So right here, this is the reducible part, and this is the irreducible part. Naturally, further discussion will focus on the reducible error. Questions so far? Okay, so this is what's going on with prediction. Now I'm going to talk about inference. Okay. Now, so for prediction, you can think of F as a black box. All right, takes in input, spits out output. And you can use the data at hand to try to simulate what that black box is doing on other data. In other words, prediction doesn't really concern itself much with what is the form of the of a function f in terms of how it depends on the data. Okay. All right. Okay. Inference, on the other hand, this is about the relationship between X and Y. Okay, so, so here we do care about the form of function F. Does F depend on certain predictors more than others? What is the most significant influence on the response? So, as far as the key questions that we ask regarding inference, okay, but I actually just mentioned the first one. Which predictors influence the response? Like the example earlier about the characteristics of a blood sample and how they're related to risk of a severe reaction from taking a drug. It may be determined that some of those characteristics of a blood sample have no bearing on that risk at all, or negligible, whereas others make a big impact. Okay. So that's one of the things that we'd like to know. Okay. Once we have a handle on which predictors are most important, what is the actual relationship between that predictor and response? So is response, what kind of function of the predictors is it? Is it an increasing or decreasing function? What's the trend? Okay. Okay. Also, what about is a relationship linear or non-linear? We like linear relationships. It's really a lot easier to work with, but what if a response doesn't really depend on the predictor in that way? So chances are we might assume a linear relationship at first and like perform solve the least squares problem. But what if that least squares solution is way off? Then that means we have a more complicated relationship between the predictors and response than that. So I return to the example of advertising budgets and how they impact sales in different markets. Okay. What media has the greatest impact on sales? Might be determined that, for instance, maybe radio advertising doesn't move a needle on sales at all. And that's certainly helpful to determine, because we think, okay, we're not going to spend any more money on radio advertising. Okay. Also, besides which media are significant at all, which media refers to the largest boost in sales. If we determine that both say TV, newspaper are significant, but which has a greater impact? Okay. Okay. Also, how much of an increase? This refers to what was often brought up in the class like Math 102 as a marginal revenue. If we're going to pour a little more money into, say, TV advertising, how are we going to? Is there diminishing returns at work, or is there something can we expect to see a significant boost from a modest amount of additional TV advertising? So we can understand the relationship between sales and add budgets on that level, then we can make a wise investment. Because this is about, you want to tweak your budget. What tweak is going to make the biggest difference? Now, if we use a linear model, then we're saying that y is approximately an affine function of x. So we have slopes multiplying each of our predictors. So these questions about the relationship between predictors and responses are answered in terms of these slopes. Are these slopes positive or negative? Which slope is the largest in absolute value? That sort of thing. Yeah, like for the first question, which of these m's are not negligibly small? For a second question, which of these are positive or negative? We're assuming linear in this case. And then given which ones are positive and not negligibly small, which of these is the largest, for the biggest increase. Right. All right. So that's the rundown on prediction versus inference. And I guess we tried a linear model first, and we found that it wasn't doing a good job of predicting. Not helping our sales much after all. Then we go back and try a nonlinear model. So, next thing to look into is how to estimate our unknown function f. So what we're given are some XY pairs. And this is referred to as training data. So they're used to construct our approximation of f that we can use to make predictions for x's that are not in the training data. The idea is we're using the data to learn what f does. Okay. Now, two approaches to constructing approximate f are parametric and non-parametric. Although it'll turn out that the term non-parametric is kind of misleading, but hopefully the distinction will be clear anyway. All right. We'll start with parametric. So the idea is make some assumption about the form of the function. For instance, we might assume that it's linear. So in this case over here, we could really it's about determining what are the coefficients and what is y naught, what is m1, m2, m3. So we reduced the problem of constructing approximate f without finding coefficients and maybe some linear combination of functions of x. It could be, you know, a linear or polynomial, something like that. Okay. Um, Here's kind of strange. Okay. Okay. Also have to be careful about putting my notation, which unfortunately was not in the notes. Okay. So. As an example. I assume a linear model. So y is equal to an affine function of your predictors. Okay. So this is approximately. All right, so then we want to find the coefficients, beta naught, beta one up to beta p, that that's fit our training data. So our training data is we have let's suppose I have n XY pairs in my training data. So we have XI1, XI2, XIP associated with YI. So the output data of a response is a scalar. Whereas the predictors, we have P, predictors is a P vector. So to find the coefficients, what we'll do is minimize the sum of squares. Okay. Yi minus is 0 plus the sum from 1 to p of beta j x I j. And this difference is squared. So we're minimizing this sum of squares. Okay, so we know how to solve this kind of problem. What kind of problem is this that we've already studied?
Least squares.
Yeah, this is a least squares problem. So we're going to minimize the 2 norm. We're trying to find vector beta that minimizes this 2 norm, where y is our, we get a column vector of all of our responses from our training data. And then the matrix X has entries Xij from our training data, the individual predictors from each of those XY pairs. And then the unknown is vector beta. Oh, wait, I goofed here. Hold on. Vector beta consists of all the unknown coefficients, beta naught up to beta p. So, oops, okay. I can rewrite the matrix. X has as its first column all ones for a beta naught term. And then the remaining columns, so this matrix is n by p plus 1, because we have p plus 1 unknown coefficients. So we have x11, x21, xn1, first predictor. And so on. Okay, so yeah, this is a full rank least squares problem. Okay. Now, how well this works depends on, did we make a wise choice on the form of our unknown function f? What if it doesn't depend linearly on the, what if response does not depend linearly on the predictors at all? Then we can go ahead and solve our least squares problem and get coefficients, but the residual will be large. Any predictions that we make by plugging some other x into our linear model would not give an accurate value of y. Okay. Now, so what you want to do is you want to reduce the reducible error. But you can do that is you can use a more flexible form. For instance, you could assume a linear and quadratic term, something like that. Allow for higher degree. So a more flexible form for f hat, which is your approximate f. Okay. But the danger in doing that, you might overfit your data. And what is meant by overfitting is your approximate f, your f hat. Your f hat captures noise in your training data, because your training data is bound to have some errors in it. Remember, y is equal to f of x plus epsilon. Epsilon might be highly, as being 0, but it might be highly oscillatory. If that creeps into your model, linear otherwise, then that's overfitting. And what that means is you may be describing the training data well, but then if you plug in some other x, again, your model's going to be way off. Yeah.
Comment about overfitting.
Uh,
And in the breads. Long time ago.
uh,
When overfitting, the model memorizes the data instead of learning from it.
that's a good way to put it. Yeah, because it's so focused on that particular data, because memorizing leaves you vulnerable to any variations. Yeah, but yeah, it's kind of like if you memorize the solutions to a bunch of calculus problems, and someone gives you a slightly different calculus problem, and you're like, I don't know what to do. Which I feel like it's how our students operate, but I've had calculus students admit to me, online homework, that if they could view an example And then they see, oh, here's what happens to the numbers in the problem. And then they get the right answer without understanding any calculus.
So
So,
they're mad at me because for his test 3 material, we're learning integration.
yeah,
I turned off all examples and the show me.
Oh,
Where
yeah.
they had to either look at the textbook or send me a message.
Mhm.
They had 2 weeks to do it. I'm like, I give you more time, this bunch of class periods, but I
Yeah,
promise you, it will help you.
yeah.
But that's the only way I finish my homework. And that's why you do terrible on the test.
Yeah, yeah, and that's what some of my colleagues would tell me, like when we started giving online homework. They write up a paper test that would have problems consistent with what's in the homework, and the students were like, I aren't too good at homework. Yeah,
Oh, that's the big complaint. My teacher never showed me how to do this.
oh, they say it all the time, yeah, it's like, yeah, we did. Like when I substitute my friend Margot Garrison in Stanford for teaching a numerical linear algebra class like this one. I'd be halfway into the term and I'd be substituting for her, and they tell me that she never taught them what a norm was. Like, yeah, she would not have left that out. Yeah. Okay. So this is parametric methods. We assume F has a particular form, and then we find the coefficients of that form. Okay, so any questions about what happened here? Yeah,
So the training data part,
yeah.
I'm not quite clear on the X components, like X11, X12. So if we have a single X1,
Uh-huh.
are we breaking that into N components?
Oh, okay. This right here refers to one of the components. So whatever X we had, whatever vector X we have, we're taking these individual components and plugging them in here.
So X1 is made up of N components.
Okay, if Y refers to your vector of N responses, then yes, it would be appropriate to think of this as the N vector of all X1s that you have. Yeah. So in fact, the system Y equals XB, that's what you would get from that kind of substitution. Yeah, okay. But yeah, the notation is kind of unfortunate here, but okay. So non-parametric. Okay. Okay. So eventually the term of non-parametric is kind of misleading. So we don't assume that our unknown function has a particular form. We're not going to assume it's linear or polynomial, something like that. But we still impose a form on F hat. So some example of what I mean by that for non-parametric fitting is we might assume that F hat is a linear combination of radial basis functions. We have some faculty here that work with those all the time. Or cubic splines. If in a one-dimensional case of Y is a function of X, where we have just single response, single predictor relationship. So this is just the 1D. Okay. So those are just a couple examples. So in terms of the mathematics, you're still solving for coefficients. But by contrast with parametric methods, non-parametric methods, they tend to use more parameters in your model. So you might use a large number of radial basis functions to get the job done. So it's kind of, it's almost like a hypocritical name. We're calling it non-parametric, but it uses more parameters. Oh, I just leave it for terms I don't come up with. Okay. That the number of parameters in the model tends to be order n, where n is the number of observations in your training data. Whereas in the example I had before, a parametric case of assuming a linear model, the number of parameters was order p, the number of components in each prediction. So we can definitely say that your f hat in a non-parametric case is more computationally expensive to come up with. And this is a personal comment, but it seems to me like there's a greater danger of overfitting. Okay. Now, so there's some criteria to consider in choosing an approach to modeling your function f. So two criteria that compete with each other. We have predictions accuracy versus model interpretability. Okay. All right. So as an example, suppose we choose a linear model. So this is a model that is likely to be less accurate, just because what are the chances that there really is a linear relationship between your response and your predictors? But it's easy to interpret. It describes a very simple relationship between your response and your predictors. You can readily tell which predictors have the most influence on the response. So it may be desirable to sacrifice some accuracy to a point anyway, in order to have a model that's easier to work with in other ways. Yeah.
Is this what a general correlation model would do? It works on this accuracy, but it's better at interpreting what has more relatability.
Yeah, I guess we're trying to determine the correlation between response and the different predictors. Yeah. So yeah, you may come up with a overly simplified relationship, but it contributes to greater understanding of the relationship between the two. Okay. So actually another example that's even less accurate but more readily interpretable than the linear model is okay. A lasso. Where that's still a linear model, but if I use a beta to refer to the coefficients like I did in the last example, only certain coefficients are even non-zero. In other words, if it's determined there's a rather negligible impact of certain predictors on the response, we'll just set its coefficients equal to 0. So the model becomes even simpler, even easier to interpret, and it gets some accuracy is given up. Um. Okay, now. More accurate. But is, less interpretable. Is a model called a generalized. Linear model. So your y hat. Is, given to be a linear combination. Of not the x's themselves, but functions of x. And those functions can be whatever. It might be higher degree polynomials, things like that. Okay. That's a whole lot more flexible than a linear model, but therefore it's going to be more difficult to interpret. It's not as easy to tell what which predictors are most significant, which ones most impact a response. That's something else to consider determining what form of a model we should use. All right. Now, everything we've talked about so far is what's called supervised. Where you have x's and y's associated with each other, and you can use those to construct some model to describe your f. Okay. Now, unsupervised learning. So your training data only has your x's, but no y's. You have a set of predictor values. Yeah, what?
No target group.
Yeah, seems kind of useless, honestly. It's like, why would anyone want to do this? But yeah, so there's not a whole lot you can do. One thing you can do is cluster analysis, where you can group your x's based on categories, and maybe these categories are associated with different response. So, but yeah, you're severely limited what you're able to do, but maybe sometimes that data is not available. Okay.
There's this example I've seen for unsupervised learning.
Yeah.
It was the data given was wine quality, and the goal was to figure out if or not it's a good quality wine, and there was no target group.
Oh, okay.
In that case, what they did was they created one based on the variables that they had, like say the percentage of tannins or acidity.
Yeah. Okay.
What was the grade or the age?
Yeah.
So that was actually, that variable changed depending on what somebody preferred as a good quality ones.
Oh, yes, very subjective.
Very subjective, yeah.
Yeah.
So that was like one.
Okay. Yeah, because you don't have a number describing goodness.
So they actually created it like a scale from 0 to 10. Like,
Yeah.
okay, everything closer to 10 is good quality.
Yeah.
Well, closer to 0 is bad quality.
Okay,
that they created based on the given variables.
yeah, well. I wonder if this would be relevant for instance, say, admissions. You have all your applicants and you have your characteristics and then you have to come up with something. But you can group them together based on like GPA brackets or
And, yeah.
things like that. And that's actually what we do. But then, yeah, you may decide that like, oh, let's not count GRE after all, things like that. Which actually is not true, The pandemic really is kind of, for us anyway, kind of put an end to, not English proficiency testing, but the use of a GRE.
I did do my GRE, but it was, I think, not that lots of it, it was over 5 years.
Oh, yeah. Well, yeah, because you came in 2020 or what? Okay, yeah, back then we weren't using it, so.
167 on fonts, I was like, I know it's old, but it.
Okay, that's good. Okay, so another contrast one paint is regression, which is what we've seen so far, versus classification. Okay. All right, so there are two kind of variables you can work with. That your responses may be quantitative, in other words, simply numerical, versus either qualitative, also referred to as categorical. So you might have either kind of response in your data, and you still have to try to find a way to work with it somehow. Quantitative variable be like temperature. Whereas qualitative, gender or day of the week. Characteristics that you could assign a numerical value to for convenience, but it wouldn't have any meaning. Yeah, because it's to be like an arbitrary assignment in that case. Okay, so if your response is quantitative, then you're able to use, as we've seen in examples, regression to come up with a fit for F. So like least squares, but all kinds of regression techniques out there. Okay. Whereas if your response is qualitative, that becomes a classification problem. All right. Now, and it's determined only by the response. It doesn't really matter so much if the predictors are qualitative or quantitative in nature, because if the predictors are qualitative, in that case, it's okay to assign numerical values to them. But it's not very helpful if you're going to do that with a response. In that case, it's called like a dummy variable. Okay. Actually, that's all I got. So yeah, we're very much just tiptoeing in to statistical learning, but.
It's giving me serious PTSD from data science days.
Okay.
It's just a joke.
Okay. Well, how do you compare that to suffering through a data science program versus suffering through a math program?
Data science program or even the job is very loose. Like you have a very, how do you say, commercial goal, but
Yeah.
it is hard for me to read because that's not the language I understand. Mainly, they use a lot of fancy words in business just to justify to do what they're doing. They want you to do something, like do something.
You'd be surprised.
But there is limitation too. And it's marketing. It's not like I'm
Yeah.
doing something like maybe working with a clinical trial, that would be different.
Mhm.
So anyway,
Yeah.
once I jumped into more mathematics, when I was doing my very last job, actually, I had to write the documentation for the company. So that was fun because I had a whole big code that I had to break down line by line and figure out what each was doing. So I could actually see the matrices.
Yeah.
It's like a 50,000 by 23,000 matrix. And I was like, okay, now getting somewhere. That was the SVD. That was better. I understand.
Okay.
Step broken down
Yeah.
and what it's doing mathematically instead of just.
Because my impression, and again, just an impression, because I haven't really gone deep into it, is it seems like neural networks, deep learning is regression of better marketing. So it's just, yeah, and what's unfortunate is that how everyone goes crazy over it, like, oh, okay, let's focus only on this to the exclusion of other math as if it never existed, and it's like, you're still using the same stuff. So, but I guess I'm not watching into that anyway. Okay, so, anyone have any questions about anything, homework problems, coding problems? Well, one more class to go. Principal component analysis. Oh, okay. Alrighty. Okay, yep, see you Thursday.
Yeah, the fast